Section 1. A universe full of surprises. The universe is vast beyond imagination. Every corner, every particle, and every motion tells a story written in light, time, gravity, and silence. Let us begin with a few of the countless wonders that make up the cosmos. The speed of light is not infinite. Light travels at approximately 299,792 kilometers per second, but it still takes time to reach us. When you look at the moon, you see it as it was about 1.3 seconds ago. The light from the sun takes 8 minutes to reach Earth, and the nearest star system, Alpha Centauri, is 4.37 light years away. This means you're seeing the past, not the present, every time you look at the sky. Space is not completely empty. We often imagine outer space as a pure vacuum, but in truth, space is filled with particles, tiny atoms, traces of hydrogen, cosmic rays, and even light from the early universe. There are around 1 atom per cubic meter in interstellar space. It's sparse, but not empty. Even in the darkest void, something remains. There is a giant cloud of alcohol in space. Near the center of our galaxy, floating in a region called Sagittarius B2, astronomers discovered a massive cloud of gas and dust, containing enough alcohol to make 400 trillion pints of beer. It's not drinkable, of course. It's methanol mixed with other complex molecules, but it reminds us the universe is full of chemical surprises. The sun makes up 99.8% of the solar system's mass. Our sun, though just a medium-sized star, is unimaginably massive. It holds 99.8% of all the mass in our solar system. All the planets, moons, asteroids, and comets combined make up only a tiny fraction. Without the sun's gravity, nothing would stay in orbit. There is a planet made of diamond. Somewhere in the constellation of Serpens, a planet orbits a dead star with incredible density. It's likely made almost entirely of crystallized carbon. A diamond the size of a planet, named PSRJ 1719-1438b. This object is a cosmic jewel. It reminds us that beauty in space often defies our expectations. Neutron stars are incredibly dense. When a massive star explodes in a supernova, its core may collapse into a neutron star, an object with more mass than the sun, compressed into a sphere just a few kilometers wide. A teaspoon of neutron star material would weigh more than Mount Everest. Their magnetic fields are billions of times stronger than Earth's, and some spin hundreds of times per second. Galaxies can collide without stars hitting. When 2 galaxies merge, billions of stars swirl together like clouds. Yet due to the vast distances between stars, they rarely collide. Instead, gravity reshapes their paths, and new stars may be born in the aftermath. In about 4 billion years, the Milky Way will collide with Andromeda. It will be a slow, beautiful dance, lasting billions of years. These are just a few of the marvels scattered across the universe. Each one opens the door to countless questions, and even more wonder. Section 2. Invisible forces and strange phenomena. Though we see stars and planets, some of the most powerful and mysterious forces in the universe are completely invisible to the human eye. This section explores the unseen architecture of the cosmos, from dark matter to cosmic expansion. Most of the universe is invisible. Only about 5% of the universe is made of ordinary matter, the kind that forms stars, planets, and people. The rest is made up of dark matter and dark energy. Dark matter exerts gravitational pull, but emits no light. We can't see it, but we know it's there because of the way galaxies move and bend light around them. Dark energy even more mysterious, is thought to be driving the accelerating expansion of the universe. Together, they make up 95% of everything that exists, yet we barely understand them. There is a limit to what we can observe. The observable universe stretches about 93 billion light-years across, but that doesn't mean it's the full size of the cosmos. Light from more distant regions hasn't had time to reach us, and may never. Beyond that limit could lie countless more galaxies, perhaps even other universes, but they remain hidden behind the cosmic horizon. The universe is expanding faster over time. Thanks to powerful telescopes and precise measurements, scientists discovered that the universe isn't just expanding, it's accelerating. This was a surprise. Gravity was expected to slow expansion over time, but something, likely dark energy, is pushing everything apart at an increasing pace. Eventually, galaxies beyond a certain distance will disappear from view entirely. Cosmic microwave background, the universe's first light. Shortly after the Big Bang, the universe was a hot, dense soup of particles. As it cooled, light was finally able to travel freely. This first light still exists today as a faint glow called the cosmic microwave background, CMB. It fills the entire sky and gives scientists a snapshot of the early universe about 380,000 years after its birth. The CMB is like a baby photo of the cosmos, cold, ancient, and filled with clues. Black holes can spin at incredible speeds. Black holes are not just gravitational traps. Some spin at nearly the speed of light. These rotating black holes can drag space-time around them, twisting everything nearby. This extreme rotation creates powerful jets of energy that can stretch for thousands of light years. Despite their violent nature, black holes help shape galaxies, acting as engines of cosmic evolution. There are more galaxies than stars in the Milky Way. The Milky Way contains over 100 billion stars. That number is vast, yet the observable universe may contain over 2 trillion galaxies. Each galaxy may host its own billions of stars, its own planets, its own mysteries. In every direction, the universe expands in richness, revealing layer after layer of complexity. The invisible forces and structures of the cosmos are as important as what we can see. They connect everything together, shaping the universe into what it is today and what it may become tomorrow. Section 3. Strange and distant worlds. Beyond our solar system lie countless planets, some familiar, others unimaginably alien. These are the exoplanets, orbiting stars far from our sun, and many of them defy the rules we once thought unbreakable. There are more planets than stars. For a long time, scientists weren't sure how common planets were, but in recent decades, space telescopes like Kepler and TESS have revealed a stunning truth. Planets are everywhere. In fact, there may be more planets than stars in our galaxy. Some stars host multiple planets, and some planets may even orbit alone, drifting through space. Billions of worlds remain waiting to be discovered. Hot Jupiters defy expectations. Some of the first exoplanets ever found were massive gas giants orbiting extremely close to their stars. These hot Jupiters complete an orbit in just days, far faster than any planet in our solar system. They're heated to thousands of degrees and often tidally locked, with one side always facing the star. Their existence challenged early models of planetary formation. How could such giants form so close to their suns? The universe, it seems, loves to surprise us. Some planets rain glass or iron on the planet HD 189733b. Winds blow at 5,400 miles per hour, and the atmosphere contains silicate particles. This means it likely rains molten glass sideways. Another world, WASP-76b, experiences iron rain. On its ultra-hot day side, metals vaporize. As the air circulates to the cooler night side, the vapor condenses and falls as droplets of iron. These are not places of comfort, but their existence stretches the imagination. Super-Earths and mini-Neptunes. Many exoplanets are larger than Earth but smaller than Neptune. These super-Earths may have thick atmospheres, liquid oceans, or rocky terrain, and some could be habitable. Others, known as mini-Neptunes, may be covered in thick gas layers with icy or liquid interiors beneath. Our solar system has no planets of these types, but the galaxy is filled with them. Rogue planets wander alone. Not all planets belong to a solar system. Some have been ejected by gravitational interactions, now floating alone through space. These rogue planets are cold, dark, and difficult to detect, but they may be numerous, perhaps even outnumbering the stars themselves. Their isolation doesn't make them lifeless. Some might retain heat, or even hidden oceans beneath icy crusts. Kepler 16b orbits. Two suns like the fictional planet Tatooine from Star Wars. Kepler 16b orbits a pair of stars. It experiences 2 sunrises and 2 sunsets each day. Binary star systems are common, and planets can form and survive in their embrace. This discovery showed us that even science fiction can become scientific fact. Each planet we discover tells us more about how varied and creative the universe can be. From boiling skies to frozen deserts, the diversity of distant worlds offers a constant reminder of how little we truly know. Section 4. Time in the Cosmos. Time governs everything, from the rhythm of our days to the life and death of stars. But in the vastness of the universe, time behaves in unexpected ways. In this section, we explore the mysterious, often counterintuitive nature of cosmic time. Time began with the Big Bang. The beginning of the universe was also the beginning of time as we know it. Before the Big Bang, there may have been no before at all. At least, not in any way we understand. Time, space, and matter all emerged together in a single expanding burst nearly 13.8 billion years ago. We measure time with light. Because light moves at a constant speed, it serves as a cosmic clock. Light years are not just distances, they are units of time. When we observe distant galaxies, we're seeing them as they were millions or even billions of years ago. Looking deeper into space is like peering back in time. Time moves differently in gravity. According to Einstein's theory of general relativity, time is affected by gravity. The stronger the gravitational field, the slower time flows. This means that near a massive object, like a black hole, time passes more slowly compared to a region with weaker gravity. It's not just theory. GPS satellites, which orbit high above Earth, need to correct for this difference in time to maintain accuracy. Black holes can stretch time. If you could orbit near the edge of a black hole, close to its event horizon, you would experience time at a much slower rate than someone far away. In theory, minutes could pass for you, while years pass elsewhere. This extreme warping of time makes black holes fascinating laboratories for physics. The oldest light is still traveling. The cosmic microwave background has been moving through space for over 13 billion years. It carries information from the infant universe and still reaches Earth today as a faint signal in every direction. This ancient light connects us to the very beginning of time. Stars live and die on cosmic timescales. Massive stars burn bright and fast, living only millions of years. Smaller stars, like red dwarfs, can burn for trillions of years. Our Sun is about 4.6 billion years old and has roughly 5 billion years left. But in the grand timeline of the cosmos, even that is just a moment. Time may end differently depending on the universe's fate. How time flows in the far future depends on how the universe evolves. If expansion continues forever, galaxies will drift apart until they vanish from view. Stars will die, and only black holes will remain, slowly evaporating until only silence is left. In this heat death, time may continue endlessly, but with nothing left to mark its passage. Alternatively, if the universe reverses its expansion, time itself could collapse, ending just as it began. Time is not just something we observe. It is woven into the structure of space, shaped by gravity, light, and motion. The more we learn, the more we realize how fluid and strange time can be beyond Earth. Section 5. The lives of stars are the engines of the universe. They create light, warmth, and the elements that make up life itself. Each star is born, evolves, and eventually dies, in a journey that spans millions or even billions of years. Let's explore the remarkable life cycles of these cosmic giants. Stars are born in clouds of gas and dust. Star formation begins in giant molecular clouds, vast regions of cold hydrogen gas and interstellar dust. Over time, gravity pulls clumps of matter together, forming dense regions called protostars. As the pressure and temperature rise, nuclear fusion ignites, and a new star is born. Some of these nurseries, like the Orion Nebula, can be seen from Earth with the naked eye. The Sun is an average star, but perfect for life. Our Sun is a G-type main sequence star. It's not the largest, hottest, or most luminous star, but it's incredibly stable. It provides the perfect amount of heat and light to support life on Earth. With an age of 4.6 billion years, the Sun is about halfway through its life. Eventually, it will grow into a red giant, then shrink into a white dwarf. Stars come in many sizes and colors. Stars range from tiny red dwarfs, cool and dim, to massive blue giants, which burn hot and bright. Color reveals a star's temperature. Blue stars are the hottest, red stars the coolest. The most massive stars live short, dramatic lives, while small stars can last for trillions of years. Some stars die in violent explosions. When a massive star exhausts its fuel, its core collapses. This triggers a supernova, a brilliant explosion that can outshine an entire galaxy. Supernovas scatter heavy elements into space, seeding future generations of stars and planets. These explosions can also leave behind neutron stars or black holes, extremely dense remnants of the original star. Neutron stars are incredibly dense. A neutron star is the collapsed core of a massive star. It packs more mass than the Sun into a sphere just a few miles wide. A single teaspoon of neutron star material would weigh billions of tons. Some neutron stars spin rapidly, emitting beams of radiation like cosmic lighthouses. These are known as pulsars. Stars create the elements of life. The universe began with mostly hydrogen and helium. All heavier elements, like carbon, oxygen, and iron, were forged inside stars. Through nuclear fusion and supernova explosions, stars created the building blocks of planets and of life itself. Every atom in your body was once part of a star. Binary stars and star clusters are common. Many stars are not alone. Binary star systems, where two stars orbit each other, are common across the galaxy. Some even exist in triple or quadruple systems. Stars also form in clusters, groups of hundreds or thousands born from the same cloud, moving together through space, from birth in glowing nebulae to death in brilliant explosions or quiet fading. Stars shape the cosmos at every scale. They are both creators and destroyers, and they are everywhere. Section 6. The mystery of black holes. Black holes are among the most enigmatic and extreme objects in the cosmos. They defy our understanding of space, time, and matter. Invisible to the eye, yet capable of shaping entire galaxies, they are both feared and revered in the world of astrophysics. Let's journey to the edge of what we know and peer into the darkness. What is a black hole? A black hole forms when an enormous amount of mass is compressed into an incredibly small space. Its gravity becomes so strong that not even light can escape its pull, which is why it appears completely black. The boundary around a black hole is called the event horizon. Once something crosses this boundary, it can never return. Black holes are born from collapsing stars. Most black holes form at the end of a massive star's life. When the core of such a star collapses under its own gravity, it can compress into an incredibly dense point, a singularity. The remaining star material may be blasted away in a supernova, leaving behind a black hole at the center. They come in different sizes. There are several types of black holes. Stellar mass black holes form from collapsing stars and usually range from a few to dozens of solar masses. Intermediate black holes are harder to detect, but may form in dense star clusters. Supermassive black holes are found at the centers of galaxies, including our own Milky Way, and can have masses billions of times greater than our Sun. Their origin is still a mystery. Black holes don't suck like a vacuum. Despite popular belief, black holes don't suck objects in. Their gravity works just like any other massive object. If the Sun were replaced by a black hole of the same mass, Earth would continue orbiting it as usual. Though, of course, without sunlight. You have to get extremely close to experience their more extreme effects. They can bend light and time. The intense gravity of a black hole warps space around it. This creates gravitational lensing, where light from background stars is bent and distorted. Time also slows down dramatically near a black hole. To a distant observer, an object falling in would appear to freeze at the event horizon. Even as, from the object's point of view, time continues normally. This effect is a real consequence of Einstein's relativity. They may power the brightest objects in the universe. When matter falls toward a black hole, it doesn't always disappear immediately. It forms a spinning disk called an accretion disk, which heats up and emits powerful radiation. In some cases, this process creates quasars, the most luminous objects in the universe, outshining entire galaxies. Ironically, some of the brightest phenomena in the cosmos are powered by the darkest. Black holes can merge and send ripples through space. When two black holes spiral into each other, they merge into one, releasing vast amounts of energy in the form of gravitational waves. These ripples in space-time were first detected in 2015, confirming a key prediction of Einstein's theory. They opened a new way to observe the universe, not with light, but with gravity itself. Black holes challenge the limits of physics. They push the boundaries of what we understand about gravity, time, and the very fabric of the universe. And yet, they may hold the answers to some of the deepest cosmic mysteries. Section 7. Strange and distant worlds. The realm of exoplanets. For centuries, humanity wondered whether other worlds like ours existed. Today, Thanks to powerful telescopes and space missions, we know that planets are common, and many are far stranger than we ever imagined. These are the exoplanets, planets that orbit stars beyond our Sun. Exoplanets are everywhere. The first confirmed exoplanet was discovered in 1992. Since then, astronomers have found over 5,000 others, with thousands more awaiting confirmation. Almost every star you see in the night sky could host its own planetary system. Our galaxy alone may contain billions of planets. The methods we use to find them. Most exoplanets are too far and too dim to see directly, but we detect them through clever techniques. The transit method observes a star's brightness dim slightly when a planet passes in front of it. The radial velocity method measures tiny wobbles in a star's motion caused by the gravitational pull of orbiting planets. And with direct imaging, we capture the faint glow of distant worlds using specialized instruments. Each discovery reveals something new, not just about planets, but about how solar systems form and evolve. There are planets unlike anything in our solar system. Some exoplanets are truly bizarre. Hot Jupiters are gas giants that orbit extremely close to their stars, with surface temperatures over 1,000 degrees Celsius. Rogue planets drift alone through space, unbound to any star. Others may be covered entirely in water, or have diamond-rich crusts, or be scorched by twin suns. One planet, named HD 189733b, has violent winds and possibly rains made of molten glass. The habitable zone and Earth-like worlds astronomers are especially interested in planets within the habitable zone, the region around a star where temperatures could allow liquid water to exist. Many such planets have been found, but habitability is complex. It depends on atmosphere, magnetic fields, rotation, and many other factors. Still, the dream of finding a second Earth is no longer just fantasy. Super-Earths and mini-Neptunes. Some of the most common exoplanets have no equivalent in our solar system. Super-Earths are rocky planets larger than Earth, possibly with stronger gravity and thicker atmospheres. Mini-Neptunes are smaller gas planets, possibly with icy or liquid layers beneath their clouds. Their diversity hints at the variety of planetary systems in the universe. Planets in binary and trinary star systems. Some exoplanets orbit not just one, but 2 or 3 stars. These systems can produce wild orbital patterns and dramatic sunrises and sunsets. Imagine standing on a planet where the sky has 2 suns rising and setting together. Such systems show how flexible nature can be when it comes to forming worlds. Could these worlds support life? We still don't know if life exists elsewhere, but exoplanet research is bringing us closer to the answer. Future missions will examine exoplanet atmospheres for signs of oxygen, methane, or other possible biosignatures. Whether we find alien microbes or simply discover how rare life might be, these distant worlds are changing how we see ourselves. Exoplanets remind us that the universe is vast, surprising, and full of possibilities. They are a testament to human curiosity and a hint that we may not be alone. Section 8. Galaxies, Cities of Stars. Galaxies are the grand cities of the universe. Enormous collections of stars, gas, dust, dark matter, and more. They come in many shapes and sizes, each telling a different story about the cosmos. In the vastness of space, galaxies are the main building blocks, and we live in just one of billions. What is a galaxy? A galaxy is a gravitationally bound system containing millions to trillions of stars. Alongside stars, galaxies contain planets, nebulae, star clusters, and clouds of gas and dust that birth new stars. invisible dark matter forms a massive halo around each galaxy, shaping its motion and structure. The Milky Way, our galactic home. Our own galaxy, the Milky Way, is a barred spiral galaxy with arms that curl gracefully through space. It spans over 100,000 light-years and contains at least 100 billion stars, including our Sun. From Earth, we see it as a milky band across the night sky. That's our view from the inside, looking into the densely packed disk. Galaxies come in many shapes. Astronomers classify galaxies into several types. Spiral galaxies have flat disks with spiral arms, like the Milky Way. Elliptical galaxies are rounded, with little structure and few young stars. Irregular galaxies lack clear shape, often due to gravitational disruptions. Each type reflects a different stage or event in a galaxy's life. Galaxies interact and collide. Galaxies are not isolated. They move through space and often interact, especially in clusters. When galaxies collide, they can merge into a single larger galaxy. Their stars usually don't collide. Space between stars is vast, but the gravitational chaos can trigger waves of new star formation. In about 4 billion years, the Milky Way will merge with the nearby Andromeda galaxy in a slow, graceful dance lasting millions of years. Supermassive black holes at their cores. Nearly every large galaxy harbors a supermassive black hole at its center. In the Milky Way, it's called Sagittarius, a star, with a mass of over 4 million suns. These black holes influence the motion of stars around them and may help regulate galaxy growth. Sometimes, as they feed on surrounding matter, they power active galactic nuclei, intensely bright centers that outshine their galaxies. Galactic clusters and cosmic webs, galaxies gather into clusters bound together by gravity. These clusters form superclusters, which weave into the cosmic web, a vast structure of filaments and voids that defines the large-scale shape of the universe. Galaxies are not just islands of stars. They're part of a grand, interconnected architecture. Galaxies evolve. Over time, galaxies change as stars are born, die, and move. They grow through mergers, and their shapes transform. Some galaxies stop forming stars and become red and dead, while others, like the Milky Way, continue to form new generations of stars. Galactic evolution spans billions of years, but each stage is a chapter in the universe's story. To gaze at galaxies is to look deep into space and time. Some are so far away that their light has taken billions of years to reach us. Each one is a glowing footprint of the universe's past and a hint of what lies ahead. Section 9. The expanding universe and the mystery of dark energy. The universe is not static. It is growing, stretching in all directions. This expansion, first discovered in the 20th century, forever changed our understanding of the cosmos. But even more mysterious is what is driving it. The answer may lie in something we still barely comprehend. Dark energy. The universe is expanding. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. Distant galaxies are moving away from us, and the farther they are, the faster they recede. This meant the universe itself is expanding. Space is not just the backdrop for matter. It is dynamic and growing. If we reverse this expansion in time, we arrive at a dense, hot origin, the Big Bang. Not just expanding, accelerating for decades, scientists assumed gravity would slow the expansion over time. But in 1998, observations of distant supernovae revealed a shocking twist. The expansion is actually speeding up. Something unseen is pushing galaxies apart with increasing force. That something has been named dark energy. What is dark energy? Dark energy is not directly observable. We infer its existence from its effects on cosmic expansion. It is thought to make up about 68% of the total energy in the universe. Yet we don't know what it is. It might be a property of space itself, a kind of vacuum energy, or it could be something else entirely. Its discovery earned a Nobel Prize in Physics in 2011, but it remains one of the greatest scientific mysteries. The fate of the universe depends on it. Dark energy isn't just a curiosity. It may determine the ultimate fate of everything. If its strength remains constant, the universe will continue expanding forever, growing colder and emptier. If it increases, expansion could accelerate so much that galaxies, stars, and even atoms are eventually torn apart in a hypothetical end called the Big Rip. Or if it fades away, gravity might eventually slow and reverse the expansion, leading to a big crunch. Each outcome depends on the true nature of dark energy. Clues from the cosmic microwave background. Astronomers study dark energy by analyzing the cosmic microwave background, the afterglow of the Big Bang. By measuring tiny variations in this ancient light, we learn about the universe's contents, geometry, and the fate. Other tools, like galaxy surveys and gravitational lensing, help map how structure in the universe has grown and how dark energy has shaped it. Still more questions than answers. Despite being the dominant force in the cosmos, dark energy is elusive. It doesn't emit light, doesn't clump like matter, and interacts only through gravity. Some scientists even wonder if it's real, or if our theories of gravity need to be rewritten. Future telescopes, like the Nancy Grace Roman Space Telescope and the Euclid mission, aim to unravel its secrets. But for now, dark energy remains a whisper in the dark, a quiet force sculpting the universe on the grandest of scales. Section 10. Looking back in time. The universe as a time machine. When we gaze at the night sky, we are not just seeing space. We are also seeing time. The universe is a time machine. Each beam of light that reaches us has traveled across vast distances, bringing with it a story from the past. Light takes time to travel light, though incredibly fast, doesn't arrive instantly. It moves at about 300,000 kilometers per second, but space is immense. The light from the moon takes just over 1 second to reach us. Light from the sun takes about 8 minutes. The nearest star system, Alpha Centauri, is 4.3 light years away. The Andromeda Galaxy, 2.5 million light years. When we look at faraway objects, we see them as they were, not as they are now. Telescopes are time machines. Astronomers use telescopes like time machines, gathering ancient light to explore cosmic history. Some telescopes peer so far that they see galaxies from when the universe was just a fraction of its current age. Space telescopes like Hubble and James Webb are helping us view the first stars and galaxies, objects formed over 13 billion years ago. In a very real sense, we are watching the universe evolve across time. The cosmic microwave background. One of the most ancient lights we can detect is the cosmic microwave background, a faint glow left over from the Big Bang itself. This light is nearly 13.8 billion years old, a remnant from when the universe was just 380,000 years young. It surrounds us in every direction, a whisper from the beginning. By studying this faint radiation, scientists gain insight into the early universe, its shape, contents, and growth. We are seeing the past, not the present. This concept is both awe-inspiring and humbling. The light we see from a star 10,000 light years away left that star long before the first cities on Earth were built. Some of the galaxies we observe may not even exist anymore. Their light still racing toward us across the darkness. In astronomy, now becomes a fluid concept. Why this matters? By looking into the distant past, we can understand how galaxies form and change, how stars are born and die, and how the elements that make up our bodies were forged in cosmic furnaces. The deeper we look, the more we uncover about our origins. Time and space are woven together, and every star in the sky is a message from a different era. As we continue exploring the universe, we are not just studying distant objects, we are learning about the history of everything. And in that vast timeline, we find our place. Section 11. The life and death of stars. Stars are not eternal. They are born, they live, and they die. Each one following a path shaped by its mass and environment. Though they seem like steady lights in the sky, stars are dynamic, changing over millions or billions of years. Their stories are the engines of cosmic evolution. Born in clouds of gas, the birth of a star begins in a nebula, a cold, dark cloud of gas and dust. Gravity pulls this matter together, causing it to collapse and heat up. Over time, a dense core forms, and when the pressure and temperature are high enough, nuclear fusion ignites. The process that powers a star. A new star is born. A balancing act. A star's life is a balance between gravity pulling inward and fusion pushing outward. This fusion converts hydrogen into helium, releasing vast amounts of energy as light and heat. This balance can last for billions of years, depending on the star's mass. Small stars like red dwarfs burn slowly and can live for trillions of years. Medium stars, like our Sun, shine for about 10 billion years. Massive stars live fast and die young, lasting only a few million years. The end depends on the mass. When a star exhausts its hydrogen fuel, the balance breaks. For Sun-like stars, the core contracts and the outer layers expand into a red giant. Eventually, the outer layers are shed, creating a glowing shell called a planetary nebula, and the core becomes a white dwarf, a dense, Earth-sized remnant that cools slowly over time. Massive stars die explosively. Massive stars end in the more violent ways. When they run out of fuel, the core collapses under its own weight, triggering a supernova, a brilliant explosion that outshines entire galaxies for a short time. What remains can become a neutron star, incredibly dense, with the mass of the Sun packed into a sphere just a few kilometers wide, or a black hole, a region of space so dense that not even light can escape its gravity. Stars create the elements. Stars are not just lights in the sky, they are cosmic forges. Inside their cores, stars create the elements that make up the universe: carbon, oxygen, iron, and more. When they die, especially in supernovae, these elements are scattered into space, seeding future stars, planets, and life. The atoms in your body were once inside stars. You are made of stardust. Star clusters and stellar families. Stars often form in groups called clusters. Some are loose and temporary, like open clusters, while others, like globular clusters, are ancient and densely packed. Studying clusters helps astronomers understand stellar evolution, since stars in the same cluster formed at the same time and from the same material. The legacy of a star. Those stars die. They leave behind legacies: white dwarfs that glow for eons, black holes that warp space and time, and elements that become new stars, planets, and even people. Each twinkle in the sky is a chapter in the universe's story. and every star that fades makes way for something new. Section 12. Black holes, gravity's deepest secret. Among the many strange and awe-inspiring features of the universe, black holes stand out as some of the most mysterious. They are places where the laws of physics break down, where gravity becomes so strong that nothing, not even light, can escape. Despite their invisibility, black holes are real, detectable, and deeply fascinating. What is a black hole? A black hole is a region in space where matter has collapsed into an incredibly dense point. The gravity is so intense that the escape velocity exceeds the speed of light. The boundary around a black hole is called the event horizon. Once something crosses this invisible line, it cannot return. We cannot see what lies inside, only what happens around it. How black holes form. Most black holes form when massive stars die. After a supernova explosion, if the core that remains is heavy enough, it collapses into a black hole. The matter is squeezed into an infinitely small space, creating what's known as a singularity. This singularity is surrounded by the event horizon, which hides its mysteries from view. Types of black holes. There are several kinds of black holes distinguished by their size and origin. Stellar black holes form from collapsing stars and usually contain a few times the mass of the Sun. Intermediate black holes may form from merging stars or dense star clusters. Supermassive black holes sit at the centers of galaxies, including our own Milky Way, and can have masses millions or billions of times that of the Sun. How supermassive black holes form remains an open question. How do we detect them? Though black holes emit no light, we can detect them through their effects. Gravitational influence on nearby stars and gas reveals their presence. Matter falling into black holes heats up and glows, producing powerful X-rays. When black holes merge, they send out ripples in space-time called gravitational waves, which we've detected using advanced instruments like LIGO. What happens inside? Inside a black hole, our current understanding of physics breaks down. The singularity is a point where density becomes infinite and space and time lose their meaning. Some theories suggest that black holes might connect to other regions of space, so-called wormholes. But this remains speculative. We cannot know for sure what lies beyond the event horizon. Black holes and time. Black holes do strange things to time. Near a black hole, gravity is so strong that time slows down, an effect predicted by Einstein's theory of general relativity. To an outside observer, an object falling into a black hole appears to slow, never quite reaching the event horizon. But for the object itself, time continues normally as it crosses the point of no return. Do black holes die? Surprisingly, black holes may not be eternal. Physicist Stephen Hawking proposed that black holes slowly lose mass by emitting Hawking radiation, a quantum effect near the event horizon. Over unimaginable spans of time, a black hole could evaporate entirely. This process is still theoretical, but it opens new questions about the fate of information and the end of even the darkest objects in the cosmos. Black holes inspire and puzzle. Black holes challenge our understanding of physics, blending gravity, quantum theory, and the fabric of space-time. They are not just destroyers, but also cosmic laboratories, places where the deepest truths of the universe may be hidden. As we continue to study them, we may uncover not just how they work, but how the universe itself is built. Section 13. Dark matter and dark energy. The invisible universe. When we look up at the night sky, we see stars, planets, and galaxies. the visible matter that makes up everything we know. But astonishingly, this visible matter accounts for less than 5% of the universe. The rest is made of things we cannot see. Dark matter and dark energy. They don't emit or reflect light, but their presence is undeniable, felt through their gravitational effects and influence on cosmic expansion. What is dark matter? Dark matter is a mysterious form of matter that does not emit, absorb, or reflect light. It's completely invisible, yet it makes up about 27% of the universe. We know it exists because of its effects. It holds galaxies together. Without dark matter, galaxies would spin apart, as their visible mass isn't enough to account for their motion. It bends light from distant objects, a phenomenon known as gravitational lensing. Though we can't see dark matter, we can observe its gravitational fingerprint on large cosmic structures. What could dark matter be? Scientists don't yet know what dark matter is made of. Some theories suggest it could consist of undiscovered particles that rarely interact with ordinary matter. Particles like WIMPs, weakly interacting massive particles, or axions. Experiments deep underground, in space, and at particle accelerators are all searching for signs of these elusive particles. So far, dark matter remains one of the greatest mysteries in physics. What is dark energy? Even more mysterious than dark matter is dark energy. It makes up about 68% of the universe and is responsible for one of the most surprising discoveries in modern cosmology: the accelerated expansion of the universe. In the late 1990s, astronomers found that distant galaxies were moving away from us faster than expected. Something was pushing the universe apart, and that something was called dark energy. The expanding universe. Since the Big Bang, the universe has been expanding. But scientists once believed that gravity would eventually slow this expansion, possibly even reversing it. Instead, dark energy appears to act like a kind of anti-gravity, causing the expansion to speed up over time. The more space there is, the more dark energy there seems to be. A runaway effect that may shape the universe's future. What might dark energy be? The true nature of dark energy is still unknown. It might be a property of space itself, a cosmological constant first proposed by Einstein. Or it could be a dynamic field that changes over time, something like quintessence. Another possibility is that our understanding of gravity and space-time is incomplete, and dark energy may point to new physics altogether. Why this matters? Though we cannot see or touch dark matter or dark energy, they shape the cosmos on the larger scales. They affect how galaxies form, how the universe evolves, and what fate awaits all of existence. Understanding them may unlock a new era of discovery, one that goes beyond the limits of current science. An invisible reality. In a very real sense, most of the universe is hidden. But by studying the stars, galaxies, and cosmic structures, we begin to reveal the outlines of this invisible reality. Dark matter and dark energy remind us that what we see is only a fraction of what truly exists. Section 14. The Multiverse. Are there other universes? We often think of the universe as the totality of everything that exists, all space, time, matter, and energy. But what if the universe is not alone? What if our cosmos is just one bubble in a vast sea of others? This is the idea of the multiverse, a concept that stretches the imagination and challenges our understanding of reality. What is the multiverse? The term multiverse refers to a theoretical collection of multiple, possibly infinite, universes. Each one may have its own laws of physics, its own constants, and perhaps even different dimensions of time and space. Some versions of the multiverse suggest that these universes are completely separate. Others propose that they might interact or even give birth to one another. Where does the idea come from? Several areas of physics and cosmology point toward the possibility of a multiverse. Quantum mechanics, with its principle of superposition, has led to the many worlds interpretation, where every possible outcome of a quantum event occurs in a separate branching universe. Cosmic inflation, the rapid expansion after the Big Bang, could lead to eternal inflation, spawning countless bubble universes, each with its own unique traits. String theory, which aims to unify all forces of nature, allows for many solutions, each corresponding to a different universe with different physical parameters. What would other universes be like? If the multiverse exists, some of the other universes might be wildly different. A universe with no stars, where gravity is too weak to form them. A cosmos where time flows in reverse. Realities with different numbers of spatial dimensions. Worlds where the constants of nature make life impossible, or more abundant. There could even be universes where history unfolded differently, where planets like Earth evolved in alternate ways. Can we ever detect other universes? One of the greatest challenges of the multiverse idea is that it may be untestable. If other universes are truly disconnected from ours, we might never observe them directly. However, some theories suggest that interactions between universes could leave subtle traces, like unusual patterns in the cosmic microwave background, the afterglow of the Big Bang. So far, no conclusive evidence has been found, but the search continues. Why the multiverse matters. Even if we never prove the multiverse exists, the idea forces us to re-examine assumptions about uniqueness and necessity. Is our universe finally tuned for life because it had to be? Or are there countless other universes, and we just happen to live in one where life is possible? These questions cut to the heart of cosmology, physics, and even philosophy. A universe among many. The multiverse stretches the boundaries of what we consider real. Though speculative, it reminds us that the cosmos may be far more vast and varied than we ever imagined. And in the silence between stars, in the quantum mysteries of existence, there may lie hints that our universe is not alone. Section 15. Cosmic time. The universe's ever-ticking clock. Time is something we all experience, yet few things are more mysterious. We feel it pass second by second, but in the grand scale of the cosmos, time moves in strange and unexpected ways. What is time really? Is it absolute? Or is it woven into the fabric of the universe itself? Let's take a journey through cosmic time, from the first moments of existence to the infinite futures that may await. The beginning of time. According to modern cosmology, time as we know it began with the Big Bang, about 13.8 billion years ago. Before that moment, space and time did not exist in any form we can understand. The Big Bang was not an explosion in space. It was an expansion of space and time itself. With it came the birth of the universe and the first tick of the cosmic clock. Time and relativity. One of the most revolutionary ideas in physics came from Albert Einstein. Time is not constant. In his theory of general relativity, time is linked with space, forming a four-dimensional fabric, space-time. Gravity can warp space-time, and that affects how time flows. Near a massive object like a planet, or especially a black hole, time runs more slowly. This means that time is relative, It depends on your location and speed. Cosmic time scales. The universe operates on timescales vastly different from our daily experience. Here are a few examples. A photon of light takes over 8 minutes to travel from the Sun to Earth. The light we see from distant galaxies may have traveled billions of years to reach us. A single orbit of the Sun around the Milky Way takes about 225 million years. The lifespan of a star can last from millions to trillions of years. Cosmic time stretches far beyond human perception, reminding us of how brief our lives truly are in comparison. Time travel and the universe. Is time travel possible? In theory, relativity allows it, at least in some forms. Traveling near the speed of light or being near intense gravity can slow down time dramatically. This is called time dilation. Some solutions in Einstein's equations even permit closed time-like curves, loops in time that could, in theory, allow time travel. But in practice, no evidence supports backward time travel, and paradoxes raise difficult questions. Still, it's an area of deep scientific and philosophical curiosity. The end of time. Not will time ever stop. In some scenarios, time continues endlessly, with the universe expanding forever into cold emptiness, known as the heat death. In others, time could end in a big crunch, or reset in a big bounce, starting the cycle again. If space and time are connected, then the end of space may also mark the end of time itself. But in the present, the cosmic clock continues to tick, relentless, silent, eternal. Time as perspective. While we measure time in seconds, minutes, and years, the universe experiences it in epochs and eons. And yet, all of it, from the birth of galaxies to the dance of atoms, happens within time's gentle flow. To understand time is to understand ourselves, how we change, how we remember, and how we belong to a universe in motion. Section 16. Ancient Astronomy. Humanity's first science. Long before telescopes or satellites, before space probes or quantum theories, humans looked up at the night sky and began to wonder. The earliest civilizations observed the movements of the stars, the sun, the moon, and the planets. And from these observations, they built calendars, myths, temples, and time itself. This was the birth of astronomy, perhaps the oldest science in human history. Skywatchers of the ancient world across the globe, ancient cultures recorded celestial patterns with surprising precision. In Mesopotamia, early astronomers tracked the moon's phases, eclipses, and planetary movements, laying the groundwork for calendars and astrology. The ancient Egyptians aligned pyramids and temples with stars like Sirius and the solstices. Stonehenge, in England, marks the summer solstice sunrise. A stone calendar carved in silence. In China, sky records date back thousands of years, including the earliest known supernova, observed in the year 1054. These early sky watchers had no modern instruments, just their eyes, patience, and deep curiosity. The Mayan cosmos. The Maya civilization of Central America developed one of the most sophisticated astronomical systems of the ancient world. They tracked the movements of Venus with remarkable accuracy and built entire temples aligned with solar and lunar events. Their calendars blended astronomy, myth, and ritual, treating time as a sacred cycle woven into the structure of the universe. Greek contributions. The ancient Greeks transformed astronomy from observation into theory. Thinkers like Pythagoras proposed a spherical Earth, while Aristotle used lunar eclipses to argue for Earth's curvature. Eratosthenes, in the 3rd century BCE, calculated Earth's circumference with astonishing accuracy, using shadows and geometry. Then came Ptolemy, whose geocentric model dominated astronomy for over 1,000 years. Though later proven incorrect, his work preserved and advanced astronomical knowledge through the centuries. Islamic Golden Age. During the medieval period, the Islamic world became a beacon of astronomical progress. Scholars in cities like Baghdad, Cordoba, and Samarkand preserved ancient Greek texts and expanded upon them. They developed astrolabes, accurate star charts, and refined planetary models. Figures like Al-Battani and Al-Tusi paved the way for later European discoveries, bridging ancient knowledge with modern science. The role of astronomy in civilization. Ancient astronomy wasn't just science, it was deeply practical. It guided agriculture, informed religious ceremonies, and shaped architecture. The skies were a giant clock, a cosmic calendar that told people when to plant, when to harvest, and when to pray. Through watching the heavens, early humans gained a sense of order, a connection to something greater than themselves, the eternal wonder. Even with today's technology, we are still sky watchers at heart. We gaze at the stars and wonder, just as our ancestors did, about our place in the cosmos. The tools have changed, but the longing to understand the universe remains timeless. In their myths, monuments, and observations, the ancients left us a message. Look up, and you will begin to understand. Section 17. Dark matter and dark energy, the invisible universe. When we look up at the night sky, we see stars, galaxies, and glowing clouds of gas. But all this, everything we can observe directly, makes up less than 5% of the universe. The rest is invisible, and yet it dominates the cosmos. Welcome to the realm of dark matter and dark energy, the unseen forces that shape the universe in ways we're only beginning to understand. What is dark matter? Dark matter is a mysterious form of matter that doesn't emit, absorb, or reflect light. We cannot see it directly. We can't touch it. We only know it's there because of its gravitational effects. Galaxies spin faster than they should. Clusters of galaxies move in ways that visible matter alone can explain. Dark matter appears to act like an invisible skeleton, holding galaxies together and shaping the large-scale structure of the universe. How do we know it exists? One of the first clues came in the 1930s, when astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving too fast to be held together by visible matter. Later, in the 1970s, Vera Rubin observed that stars in spiral galaxies orbit at nearly constant speeds, defying Newtonian expectations. The explanation, something unseen, dark matter, was adding mass. Today, computer simulations of the universe's formation only match real observations when dark matter is included. What is it made of? No one knows for sure. Dark matter is not made of atoms. It doesn't interact with light or electromagnetism. The leading candidates are hypothetical particles such as WIMPs, weakly interacting massive particles, or axions, which have yet to be detected. Experiments deep underground and in space are searching for these particles, but so far, they remain elusive. Enter dark energy. If dark matter holds the universe together, dark energy is tearing it apart. In the late 1990s, two teams of astronomers discovered something astonishing. The universe's expansion is accelerating. This meant that some unknown force, a kind of anti-gravity, was pushing galaxies apart. This repulsive energy, called dark energy, makes up about 70% of the universe. The nature of dark energy. Dark energy remains one of the deepest mysteries in science. Some theories suggest it is a property of space itself. a kind of cosmological constant, as Einstein once proposed. Others view it as a dynamic field, changing over time and space. No one knows its true origin or behavior. We only know its effects, an ever-accelerating expansion, leading the universe into a cold, diffuse future. Together, the unknown reigns. Between dark matter and dark energy, 95% of the universe is made of things we cannot see, cannot touch, and do not yet understand. This humbling truth reminds us that even with our greatest technologies, we've only just begun to uncover the full picture of reality. The beauty of the unseen. In a way, the darkness is beautiful. It means there are still vast frontiers to explore. The universe still holds secrets, and we are invited to seek them. As we peer deeper into the cosmos, we are not just mapping what we can see, but imagining what lies beyond. Section 18, Extreme Worlds. The strangest planets in the universe. In recent decades, the search for exoplanets, planets orbiting stars beyond our sun, has revealed a universe far more diverse than we ever imagined. Thanks to missions like Kepler and TESS, we now know of thousands of these distant worlds. Some are rocky, like Earth. Others are gas giants, like Jupiter. And some defy classification altogether. Let's journey to some of the strangest and most extreme planets ever discovered. HD 189733b. The Raining Glass Planet, located about 64 light-years from Earth. HD 189733b is a deep blue gas giant that may look serene from afar, but up close, it's anything but peaceful. This planet is known for winds up to 5,400 miles per hour and rains of molten glass that fall sideways, driven by supersonic storms. Its color comes from silicate particles in its atmosphere, giving it the appearance of a blue marble hiding chaos beneath. WASP 12b. A planet being eaten, WASP 12b orbits its star so closely that a year there lasts just about one Earth day. It is being slowly devoured by its star's gravity, stretched into an egg-like shape and losing its atmosphere into space. This process may eventually destroy the planet entirely. A reminder that not all worlds are safe and stable. 55 Cancri A. The Diamond Planet. This rocky planet, about 40 light-years away, has a surface temperature over 2,000 degrees Celsius, 3,600 degrees Fahrenheit. But what makes it truly fascinating is its possible composition. Scientists believe it may be made largely of carbon, and under intense pressure, that carbon could take the form of crystalline diamond. If true, 55 Cancri A may be one of the most valuable planets in the galaxy, though completely inhospitable. Tres 2b, the darkest planet. Some planets shine, but Tres 2b absorbs more than 99% of the light that hits it. It reflects almost nothing, making it blacker than coal. It orbits close to its star, glowing faintly with a reddish hue due to its high temperature, like a burning ember in the dark. Its exact composition remains unknown, but its darkness makes it one of the most eerie worlds we've found. Kepler 16b, the Tatooine planet. In a scene straight out of science fiction, Kepler 16b orbits two suns. Like the fictional planet Tatooine from Star Wars, this real-world planet experiences double sunrises and sunsets. Though it's a coal gas giant, its orbit in a binary star system offers a glimpse into the diverse architecture of planetary systems. PSRB 1620-26b. The Methuselah planet. Nicknamed the Methuselah planet, this ancient world is about 13 billion years old, nearly as old as the universe itself. It orbits a pair of dead stars. a white dwarf and a neutron star in a strange and exotic corner of the galaxy. Its survival through multiple cosmic catastrophes makes it a true survivor of the universe, a universe of possibilities. These planets remind us that the universe is filled with surprises. Some are violent and chaotic, others mysterious and ancient. Each world is a chapter in the cosmic story, an expression of what's possible in a universe governed by the same laws, but shaped by infinite variation. And for every strange world we've found, there are countless more waiting in the silent dark. Section 19. Gravitational waves, listening to the universe. For centuries, astronomy relied on light, visible, radio, X-ray, and beyond. But in 2015, humanity opened an entirely new window to observe the cosmos, not with light, but with ripples in space-time. These are called gravitational waves, and they have changed the way we study the universe. A prediction by Einstein. Over a century ago, in 1916, Albert Einstein predicted the existence of gravitational waves as a consequence of his general theory of relativity. He described how massive objects bend the very fabric of space and time. When these objects move suddenly, like when two black holes collide, they send out ripples through space-time itself. Einstein believed these waves were real, but thought they'd be far too faint to ever detect. The breakthrough of LIGO, nearly 100 years later, in a historic announcement on February 11, 2016, scientists at the LIGO Observatory revealed the first detection of gravitational waves. Two black holes, each over 30 times the mass of the Sun, had collided over 1 billion light-years away. Their violent merger sent waves that travel through the universe, stretching and squeezing space itself, and finally reached Earth. The signal was faint, changing distances by less than a fraction of the width of a proton. But it was real. How gravitational waves work. Gravitational waves travel at the speed of light, but they carry information about events we could never witness with light alone. They are produced by cataclysmic events like black hole mergers, neutron-star collisions, supernova explosions, even the Big Bang itself. Because they pass through matter almost undisturbed, they allow us to observe regions of the universe that would otherwise be hidden. A new form of astronomy, gravitational wave observatories, like LIGO in the US and Virgo in Europe, now work together to pinpoint the origins of these waves. In 2017, astronomers detected a neutron star collision and for the first time combined gravitational wave data with traditional telescopes. This event not only confirmed theories about heavy element creation like gold and platinum, but also demonstrated the power of multi-messenger astronomy. We had not just seen the universe, we had heard it. Listening to the cosmos, gravitational waves are quiet and subtle, yet they speak of the most violent, dramatic events in the universe. They tell us about black holes we cannot see, about dead stars dancing in their final moments, about cosmic cataclysms billions of years in the past. And each wave adds to a growing symphony, a deeper, richer understanding of how the cosmos works. The future of gravitational wave science projects like LISA, a future space-based detector, will extend our listening power even further, allowing us to hear lower frequency waves from supermassive black hole mergers and more. We are still in the early days of this new field, but already gravitational waves have transformed our view of the universe. They are whispers from the cosmos, and we are learning, slowly, how to understand their language. Section 20. The cosmic perspective. Our place among the stars. In all our explorations of stars, planets, and galaxies, perhaps the most profound discovery has not been about the universe itself, but about our place within it. We are made of stardust, literally. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in the hearts of ancient stars, then scattered across space in supernova explosions. We are not merely observers of the cosmos. We are a part of it. The pale blue dot. In 1990, the Voyager 1 spacecraft, already beyond the orbit of Neptune, turned its camera back toward Earth. In the image it captured, Earth was a tiny speck, less than a pixel wide, a pale blue dot floating in the vast blackness. Astronomer Carl Sagan reflected on this image, reminding us that every person who has ever lived did so on that little dot, a fragile world suspended in a sunbeam. This perspective humbles us, but also connects us to each other and to the universe that made us. The unity of the cosmos. Across countless light years, through billions of years of cosmic history, there is a remarkable unity. The same laws of physics apply to the farthest galaxies as they do to atoms in your body. The universe is not just vast, it is coherent, elegant, and knowable. This unity invites exploration, and with each new discovery, we come closer to understanding the fabric of reality itself. A journey without end. The universe is still expanding. Stars are still forming. Galaxies are still colliding. And human curiosity continues to reach outward. From ancient stargazers to modern space telescopes, our species has always looked to the sky and wondered what lies beyond. In doing so, we've not only discovered the cosmos, we've discovered ourselves.